Every encrypted message, every bank transfer, and every state secret currently relies on a specific computational barrier. We assume this barrier is permanent, but Shor's work ensures our current standards for security have a definite expiration date. This entire infrastructure depends on the immense difficulty of prime factorization. It is the mathematical foundation that keeps our private data private. As you can see here, prime factorization is easy in one direction, but extremely difficult in the other. Multiplying two large primes is a trivial task for any computer, but reversing that process to find the original factors causes the system to stall. For a modern supercomputer, trying to find those original factors is a brute force effort that would require millions of years of continuous calculation. Global commerce and digital trust currently function only because the time required to solve this specific math problem is longer than a human lifespan. In 1994, mathematician Peter Shor published a breakthrough that changed the trajectory of the field. He demonstrated that while factoring large numbers might be impossible for the machines we use today, it is a solvable task for a device that follows different physical rules. Shor's algorithm proved that a sufficiently powerful quantum computer could reduce a million-year calculation into a process that takes only a few minutes. Most of the digital world continues to use the same encryption standards today, even though the mathematical blueprint to bypass them has been public knowledge for 30 years. By turning a physical impossibility into a hardware challenge, Shor's math placed a time limit on the reliability of our current digital protections. Running this algorithm requires hardware that can manipulate matter at the subatomic level, replacing binary bits with qubits. Qubits utilize superposition, a state where a particle isn't restricted to 0 or 1, but can exist as a mixture of both states at the same time. A classical computer attempts to solve a complex problem like a person walking through a maze. It tests one path, hits a dead end, and has to backtrack before trying the next. Because of superposition, a quantum system can navigate that maze by flowing through every path simultaneously, exploring the entire structure in a single moment. This shift allows the machine to ignore the linear limitations of traditional trial and error. Simply occupying every path isn't enough to get the answer. The computer still needs a way to identify which of those infinite paths is the correct one. This illustrates quantum interference. The algorithm coordinates the qubits so waves representing incorrect answers, mathematical dead ends, collide and cancel out. Simultaneously, correct waves align, amplifying the right answer. When the machine finally measures the system, the amplified wave collapses, instantly identifying the correct primes and bypassing millions of years of standard work. The immediate consequence of this efficiency is that the mathematical barriers guarding our infrastructure become transparent. Shor's algorithm demonstrates that the same mechanics that can dismantle our current security are also the mechanics required to build a different type of computational future. The ability to factor massive numbers is just one application of this technology. The same level of processing power is required to solve some of the most complex challenges in biology and physics. By running perfect simulations of molecular behavior, researchers can map how new chemicals interact with the body, which can accelerate the discovery of targeted drugs. This system could also optimize global logistics in real time, coordinating planetary-scale supply chains that are currently too complex for our fastest supercomputers to manage. We could potentially use these machines to engineer materials at the atomic level, creating new catalysts specifically designed to capture greenhouse gases from the atmosphere. These breakthroughs suggest that the scale of quantum computation is not just about breaking existing systems, but about modeling the natural world with a precision that was previously impossible. With the transition to this new era approaching, the question shifts from if encryption will fail to how we will adapt our infrastructure to survive it. This has led to the development of post-quantum cryptography, a global effort to build a new layer of protection that is resistant to quantum interference. These new systems replace prime factorization with entirely different mathematical frameworks, such as lattice-based structures, that remain difficult for even a quantum machine to navigate. We are currently in a high-stakes race to deploy these new protections before the first large-scale quantum processors are ready for operation. Shor's algorithm forces us to confront the fragility of our current digital foundations. By addressing these vulnerabilities now, we can ensure this transition leads to a more resilient era of digital trust.